So in the previous video, we talked about projections and what projections look like and the length of them. In this video, we're going to sort of take it to the next level. Say I ask you for the projection of this vector here, A, on vector B. We know that it's going to look like that. It's going to be 7 units long. But what if we wanted to express this projection as its own vector? So I'm going to do this in, let's choose different, like green. Why not? Let's use green. So instead of this just looking at the length of that projection, what if we looked at the projection as a vector? Okay, so like that would be the projection there, and it's going to start in the same place that the vector that's projected on starts. So it's going to go from here to here. So the projection for B on A in this case would be, we know it's this line here, right? It's this projected from B, this is basically projected onto here. So if we wanted to express that as a vector, the vector would look like this. Notice here how the vector of the projection is it's very similar to A, because A is this whole line right here. It's just a little bit shorter. And in this case here, the projected vector is in the same direction as B, it's just a little bit shorter. So that's a little bit of a trend here. So what would it look like? Let's just go through the rest of them to see what it looks like. So here, for this next one over here, the projected A on B is this length here, but if we wanted to express that as a vector, the vector projection would look like that, right? It'd be longer than B originally was, right? Same thing here. If we look at the projection of B on A here, the projection vector would look like that. So again, it's in the same direction of A, it's just a little bit shorter. And that's the pattern. Basically, the projected vector is going to be in the same direction as your vector that's projected onto. It's just going to be a different length, longer or shorter. I mean, it could technically be the same length, but it's not likely that that's the case. So here, this represents the vector of the projection. Here, this represents the vector of the projection. It goes this way because, I know you might be tempted to go this way because A goes in this direction, but we're looking at where B starts, the thing that's projected onto, where that starts. So all the vectors basically start here, so let's start there with our projection as well, okay? And yeah, here we go, we have 0, the 0 vector here, so there's no vector here and there's no vector here. So how do we find that vector now? By now everyone should know how to find the length of that projection, so basically the magnitude of that vector, but how do we find the x and the y component of that vector so we can express it as a vector as opposed to just a length? That's what this video is going to talk about. So if we look back at our previous question, so this is on the next page, page 35 at the bottom. You'll notice it continues on from where we left off before. So how can we express the vector that represents the projections? So here we're projecting A onto B. So that's going to look like this, where this is a right angle. And the length of the vector is this, which we already found. We found that length of the vector, if we go back up to that previous question, was 22 over root 37. That was the exact answer. Let's stick with that, 22 over root 37. So this is 22 over root 37. And we would call this the projection of A on B. Okay, so that's the length of the projection. Now the question for today is, how do we express this projection as a vector? So remember, when we express a vector, we usually want like the x component and the y component, right? Or we want a magnitude and direction. Either one of those would be fine because they're two different ways to express vectors. So how can we do that? And there are a bunch of ways to do it. Like you could just do it geometrically by looking at it. If you know the length, you know the angle between them. We found that before. You can do all sorts of fancy stuff, fancy geometry to basically figure it out. But there actually is a bit of a shortcut method. And it involves using this projection length that we already found. So it takes into account the fact that a vector B is the same direction as our projection vector, right? Always, because we're projecting onto vector B. So the projection is always going to be in the same direction as B, or going in the opposite direction, either way, in which case it's negative, but it's on that same line as vector B, and we make use of that fact to help us out here. So the way we do it is like this. Vector B has a certain length, right? We don't know. It could be longer than the projection, it could be shorter than the projection, but it has a certain length. This is a bit of a problem because in this case, what we essentially want to do is we want to scale down this big vector B here, which looks like this. Let me just copy it out. So it's going to look like this. This is our vector B. We basically want to shrink it down, right? We want to shrink it down so it's the length of the projection, right? We want to shrink it down. So this is the projection of A on B. And we put an arrow on top of it when it's represented as a vector. That's the only difference. So we want to basically scale it down, but we need to figure out how much to scale it down by. Remember, one thing we can do is we can multiply vectors by numbers to make them longer or shorter. Like if we multiplied B by 2, we would get a vector that's twice as long. If we multiplied B by, let me erase that. If we multiply B by a half, we'd get a vector that's half as long, right? Which in this case looks like it's sort of like the projected vector is like a little bit more than half, right? Maybe it's 2/3 of the whole thing. So how do we find out exactly how much to scale it down or up by? Well, I made you watch a video that I made about normalizing vectors. And there's a reason I gave you that video, and it's because we can use it here. So remember what it means to normalize a vector. Normalizing a vector means making the length of a vector 1. So taking a vector, for example, vector B here, and I'm actually going to move that. Can I move it? Can I move it? Oh, sort of. Hold on. Let me grab that. And I'm going to move it over here. There we go. So I basically just copied that vector over here. If we can take that vector and shrink it down to a length of 1, that might help us. That's what normalizing is. So it's taking B basically and shrinking it down so it has a length of 1. So how do we do that? So in order to find the unit vector in the direction of B, remember the unit vector means it has a length of 1 and has a little hat on it. To find that, we do vector B over the magnitude of vector B. Because it's basically like you're dividing by itself, so you're basically shrinking it down to 1. So vector B we know is, what is it? It is over 1, 2, 3, 4, 5, 6. So it's over 6, and it's up 1. And we're going to divide by the magnitude. The magnitude is going to be root 37, right? Because it's going to be 6 squared plus 1 squared, and take the square root of that, which is root 37. So vector B basically, or the unit vector in the direction of B, we can just divide each of those terms by 37, root 37. So it's going to be 6 over root 37 and 1 over root 37. So this new vector, so notice how B started off as, actually let's just put that, we should put that down here. B is 6, 1. This is what we're trying to find. We don't know what that vector is. But now what we know is we know a unit vector in that same direction. So keep in mind, the unit vector, the projected vector, and vector B are all in the same line, right? They're all collinear, they're all parallel to each other essentially. So this one is nice because it's basically like we've shrunk down that vector to a length of 1. And now if we wanted to find a vector of any length in that direction, we could just multiply it by a scalar, by a number, right? Think about it. We found, so this has a length of 1, right? This has a length of 1. So in order to find a vector in that same direction with a length of 5, for example, all we need to do is multiply this unit vector by 5. Say we wanted to find a vector in that same direction with a length of 10. All we would need to do is multiply this by 10. So in order to find this vector, all we need to know is the length of this vector, the projected vector. Once we know that, we can just multiply this unit vector by the length of the projected vector to give us the vector that represents that projection. So that's all we got to do. So to find the projection of A on B, the vector of the projection, it's just going to be basically it's our length, which we calculated that earlier in the previous question, 22 over root 37 times 6 over root 37, 1 over root 37. We multiply it by the unit vector. Now we can simplify. Each of those terms is basically a fraction, so we're going to do 22 times 6. Where is my calculator? Oh, I found the calculator. There we go. So we're basically just going to simplify that. 22. So basically we're just going to multiply this times each of these components, right? So 22 times 6 is 132. Oops. And then we're going to multiply, we're going to multiply the root 37 by root 37, which is just root 37, right? Root 37 times root 37 is just 37. And then we're going to multiply 22 times 1, which is just 22 over 37. So I can do that. I can check, and can I reduce that? I don't think I can reduce that. I think 37 is a prime number that cannot be divided. Yeah, that's right. So that's our new vector, the projection of A on B. And we can check, like if you weren't sure, you could check to see if this length, if we found the magnitude of this, it comes out to this, 22 over root 37. You can trust me, or you can try it yourself to see if it's true, but it should work, right? So we basically now know a vector in that direction. To simplify this, so we don't have to think about that every time, notice how I put formulas for this at the bottom of the page. And you should notice something right away about these formulas. First of all, there's two ways to calculate it. Well, I mean, it's actually the same way. I just showed one of them simplified. So basically what this one is, it's, oops, erase that. It's this part here, and there's two parts to it. There's this part here and this part here. Do you recognize this part here? Well, notice how, if we go back to the previous page, that was just our formula for the projection of a vector, the length of the projection, right? There you go. So that is part of our formula, and all we do is we multiply it by the unit vector in the direction of B, right? Because that's exactly what we did here, to scale it up. So basically the unit vector scales it down to 1, to a length of 1, and then this part scales it up to the length of the projection. Now, to rewrite that, you can write it because the unit vector of B is just B over the magnitude of B. So you can sort of rewrite it like this. So essentially, to find it, the quick way we're always going to do this is A dot B times B over the magnitude of B squared, right? So if you know the magnitude of B squared, you know A dot B, you basically, those are sort of the constants that you're just going to multiply by vector B. Now notice, B is the thing that's being projected onto. And if you want to memorize this formula, it's a good formula to know. After you've done a bunch of practice questions, it should be pretty easy for you to have this memorized, basically. But if we, for example, were projecting B on A, notice how those things have to flip around, right? The dot product doesn't, because the dot product of A dot B and B dot A is the same thing. But if we wanted to sort of swap it around, we could swap around everything. We don't have to do it for that. But this is going to be over A times the unit vector of A, right? If we were flipping it around. And the same thing here, if we were flipping it around, if we were trying to find the projection of B on A, it's not the same thing. It's a different answer. Remember, we talked about that in the previous video, but it's basically going to be B dot A over the magnitude of A times, oops, see, that's wrong. It should be, got to switch it to A, the unit vector of A, which is A over the magnitude of A. Okay? So there you go. That's the shortcut for basically finding the projection of any two vector, a vector onto another vector, and this is the vector representation of it. So if you only need the length of the projection, you're going to use the other formula, which is just basically this part. But if you want the vector representing that projection, you're going to use the whole thing. Okay? So really, you don't need to memorize this formula and that other formula separately. If you just memorize this one, then you're good to go. Okay? All right, so let's just look at the next question using the same idea. And by the way, this works for any dimensions, as you can probably guess, because we're just taking the dot product, which works for any dimensions. We're just finding unit vectors, which same thing for any dimensions. So this works in 2 dimensions, 3 dimensions, infinite dimensions. Okay, actually I don't know if it works for infinity dimensions. There's no such thing as that though. All right, so what I want you to do is I want you to try this. Just exactly what we just did. I want you to try this with two new vectors. So projecting Q onto R and R onto Q. Find the vector projection of these two things using that formula. Okay, so pause the video here. Try it. When you're done, unpause the video. I'm going to reveal the answer. Okay, so here's the solution. You'll notice the solution to A, the projection of Q and R, is 52 over 17 and negative 13 over 17. And the projection R on Q is 52 over 25 and 39 over 25. Remember also that this part represents the magnitude of that vector, right? The length of that vector, which in this case is the length of the projection, right? So 13 over 5 is the length of this projection, and 13 over root 17 is the length of this projection. So that's also useful that piece of information is also there, which is why I separate these out and don't just square them usually, just because it sort of explains what you're doing as you're doing it. So there you go. This works in 2D, 3D, 4D, as many dimensions as you want, okay? I'll leave example 4 as a problem to do together in class.